Hi, good morning, everyone. I'm apologizing in advance. My voice has been getting worse, and my goal is to get through this lecture good, and then I'll play the rest of the day by ear. Um, Yesterday, I ended up playing back your lecture from Monday because for my last class because they couldn't understand me. And it's like I said on Monday, it's just a sinus infection, but it's affecting my voice. So anyway, today we're going to look at hash tables. And hash tables is a method of storing our data in an array, or it could be an array of lists, trees, etc., heaps, um, using a an arithmetic formula. So it's not a comparison type thing at all. We're not sorting things alphabetically. We're using some kind of a formula to put things into these tables. So it's an arithmetic formula. Okay, now the goal, we're not going to actually achieve this goal, but the goal is to have theta 1 look up, insert, delete. This is not generally practical. Um, so we will minimize. So that the average is theta 1. Or a log n. Okay, so now when I say we're using an arithmetic formula, this could be as simple as index an array Now, you're going to see why this is not practical. But if I could index an array of size 10 to the ninth power and use social security numbers, that's definitely unique. So it's clearly theta 1. Of course, what's the problem with using an array of size 10 to the ninth power to store my data? Say I want to make sure every single student in my class has a unique place in the array. So I'm going to index you by your social security number. So I'm going to make an array of size 10 to the ninth power. And how many students do I have? Let's take all my data structure students, 145. That's pretty ridiculous, right? Hello? Hi? Anyone out there? Can you hear me? Is just not talking to me? I'm getting hurt feelings this last week or two. People not talking to me. I mean, clearly that would be a ridiculous sized array to hold 100 people. But that would definitely be unique. It's got way too much wasted space. I could use your CUNY ID. But that's still 8 digits, right? Now, kind of a standard thing is, and you know, if you've called any of your banks or credit cards or anything like that, a lot of places use the last 4 digits of your social security number. So that's 10 to the 4th locations. Now, again, depending on how many people I'm storing, it's certainly not as bad as using the social security number. Hold on one second. Um, so if I were using your CUNY ID number for the 100 students, I'm still wasting a lot of space. But it's unique. I'm certainly not wasting the kind of space I would with your social security number. I could use the last 4 digits of your CUNY ID also. No matter what I do with this idea, the last 4 digits of something, is this going to guarantee a unique mapping? I mean, is it possible that if I went with either the last 4 digits of your social security or the last 4 digits of your CUNY ID, that 2 people would have the same last 4 digits? Yeah, I mean, it may not be that likely, but it's definitely possible. I had a situation, it was at Queens, it was a big class. It was a 220, and I had about 70 students in it. I had 3 students with the same name. They spelled their first names differently, but they were the same first name. 2 of the 3 had the same last 4 digits. Now, at that time, we didn't have CUNY IDs yet. We used social security numbers, but we only saw the last 4 digits. So I had 2 of the 3 had the same last 4 digits. And the grading sheet that we had at the time, it was still paper, only had a last name, a first initial, and the 4 digits. Unfortunately, my grade sheet where I kept everything didn't have the 4 digits on it. My Excel sheet just had the names. And, you know, as a result, nobody got the right grade. The funny thing was the student who should have had an A and got a C contacted me immediately. And the student who should have had a C and got an F contacted me immediately. But the one who got an A instead of the F he so richly deserved, I never heard from him. I was certainly able to figure it out because I told registrar I needed the full names so I could check the first names. But it is possible to have, even in a class of 70 or 100 people, that 2 people could have the same last 4 digits. It's one of the things you study in 220 a little bit. I mean, 220, clearly the pigeonhole principle says if you have 100 slots and 101 people, there's a duplicate somewhere. But then there's also the thing I forget what the name of it'll come to me. But they do the theorem where they show you if you drop sticks randomly, they start to overlap one another. Even though there's plenty of empty floor space, some sticks will land on top of each other. A typical question, and there's no way I could do it with the number of people coming to class, but a typical example of this, and people are asking me about an extra credit. This is something I will give you an extra credit to do the code for, if you write the program. I'll put that up today. Did that perk people up? Did ears perk? Okay, the question is, if I were to create, I mean, this is the real question. It's not what the code will be, but if I were to decide that I'm going to store you in a hash table, not by your name and not by your ID number, but by your birthday, not the year. If I include the year, we're going to have a lot of collisions if I put you in a table by the year you were born, because most of you were born probably somewhere between, let's see, what is it, 21, 22. So most of you were born somewhere maybe between 1999 and 2004, or 1998 and 2004. That's letting some of you, have gone part-time or worked, and some of you came right out of high school. But you're mostly born in the same years. So that's going to be a problem. But if I put you into an array just by the month and day you were born, how many people do I have to have in the room before we'll have two people with the same birthday? Now you may think, all right, so let's go with 365. We won't worry about the leap year day. They can celebrate their birthday on March 1st. Unless it's the year they get their driver's license or can drink, then they'll go with February 28th. But usually they go with March 1st. So other than that, let's go 365 days a year. What do you think is the problem? Well, how many students do you think would have to be in the room before, let's say, I got a 50% chance that two of you have the same birthday? Let's take a wild guess. Have 365 days. So how many people do you think I would have to put in this table before two people had the same birthday? Yeah, 180 makes sense, right? 182, half of the days. So once I go past 180, the odds are kind of stacking up. The two people have the same day. Does that make sense to everyone? Poll time, because nobody wants to talk to me, so that's okay. I'm not going to be offended. I know you want me to be happy and loving you when I'm making up the final and not feeling all hurt and ignored and unloved. 8 of you, pick a yes or a no. I can deal with the usual 4 ignoring me. Oh, wow, 3. Getting better. Okay, so it seems pretty much all of you are good with 180. Eh. Surprisingly enough, and it's surprising, but when you run the program, you'll see the number come up. At 22, between 22 and 23, I cross the 50% probability of two people having the same birthday. That sounds wild, but it's true. And at 45 people, it's 95% sure that two people have the same birthday. When I first was told this back when I was in college, one of my teachers had a friend who, this is how he spent his weekends. He'd go into bars, and if there was 30 people or so, he'd bet everybody $1 that there were two people with the same birthday. People figured that was a pretty sure bet, particularly like after a couple of hours at a bar. And so they would go in on it, and most of the time he won. And if there was 40 people, he was almost guaranteed to win. It's just the way probabilities work. That, as soon as I've got 3 people in the room, I've already knocked 3 days out of the year that I can't use. 4 people, we've knocked 4 days out. By 22, the probability is 50%. 22 and between 22 and 23, it crosses the 50% line. So it's like really wild. So I'll give you the code to I'll ask you to write the code to calculate the probability. It's a little tricky because you can't just do the formula from probability theory, because the runtime, the numbers get too big or too small. Once you hit, I mean, you're talking about a factorial or an NCR thing. And if you calculate that with the formula for NCR, you're going to get overflow errors or underflow errors. The numbers are too big, or you're dividing by something too big. So anyway, I'll put that up. And it's just something you would do with a while loop to test when you hit 50%. So anyway, this, even though it's not likely, if I go with something like this, where it's not a unique assignment, Social Security numbers are unique. They can't duplicate them. So this may have what we call a collision. So this is what we have to talk about with the idea of using a hash table. So let's first of all just get the idea of using a hash table. Now, this should remind, what does this remind you of? This idea of putting stuff into an array by some kind of arithmetic formula. Did we do something like that on Monday? Yeah, when we did the radix sort. I should really come up with a number before I go on with this. Oh, I don't want to use that number. I just do a quick check on those numbers. Okay. So I'm going to use the formula x mod 7 to assign these things into an array. I did it again. I counted too many. I felt myself doing it. 1, 2. Okay. So each of these numbers, I'm going to find the location. So 87, let me use the purple color. I'm going to map 87 into 87 mod 7, which is what? 87 mod 7? That's a 7. Well, 7 goes into 87 how many times? Yeah, the leftover is 3. Remember, mod is just the remainder. So 87 is going to come into this element. Well, right now I haven't really discussed any problems yet. 32. 32 mod 7 is 4. 79. 2. 70. Okay, got that one good. 18. Uh-oh. What am I going to do here? And you know what? I'm going to have a problem with 3 also, because 3 mod 7 is 3. Okay. So we have a problem. I have plenty of room. So this is called a collision. What do I do with the collision? All right, now here's what we're going to, there's lots of different ways to handle this. I'm looking at 3. Okay, so these are the 3 top ideas. The first one is something called a closed hash, which is on a collision, overwrite the current value. Okay, so under a closed hash, I'm going to use green for the closed hash. Under the closed hash, on the collision, so 18 has to map to 4, to H sub 4. 32 is already there. Goodbye, 32. Replace it with 18. 3 maps to 3. 87's already there. Too bad, 87. You're gone. And 3 is in your place. This remind you of anything? Any of you take 343 yet? I can't see your names, so I don't know if there's anyone I should be yelling at. Oh yeah, I see some people I should be yelling at. What does this remind you of from 343? The cache on the direct map. So those of you who haven't taken it yet, this is what you use in when you're carrying variables, carrying data from the RAM into your cache memory, your fast access. If you're using what's called a direct mapping, when you move things into the cache, you just overwrite what's already there. Now, what's the problem with that? I mean, what's the obvious problem looking at this table? Yeah, I lost 87 and 32. They're gone. Oh, well, too bad. Which is why we have another idea. So this is idea 1, a closed hash. Idea 2, we're going to call a linear probe. Now, there's also quadratic probes. On a collision, search the array for, now this depends on an operating system idea, for the next empty location. Usually from the X mod whatever, in this case 7. So let me just fast redraw this table. So we were good on 70, 79, 87, 32. 70, 79, 87, 32. I'm going to go to a different color for the linear. So on the linear, we hit our collision with H of 4. H sub 4 is supposed to be getting a new value of 18, and H sub 3 was getting a new value of 3. All right, so on a linear probe, when I map 18, 18 is supposed to go to 4, but 4 is already full. So I'm going to start searching. Starting from spot 4. That was full. So let me look for an empty spot to go plop in. Oh, 5 is empty. Here I go. Yay. So now 18 is going to be in 5 instead of 4. And now let's look for H of 3. H of 3. 3 is supposed to go into H sub 3. No. So I start my probe. No. 32 is in there. So I move again. No. 18 is in there. So I move again. Yay. All right, so I didn't lose anything. Yay. That's good. Everything's still in here. Here's my problem. To find if, say, 79 is in the table. What am I going to do? Right, how am I going to search for it? Exactly. All I have to do is check H79 mod 7, or H2. Yes, 79 is in there. I'm good. Done. Yay. If I come up to this original closed hash, and I want to find out, is 87 in the table? Is it? No, it's not in it. Simple answer, no. In one step, I got my answer. Right? That was theta 1. Definitely theta 1. '79 was good. This was theta 1. Oops. Wrong color. All right, what about 87? On the linear probe? Yes. How did I know? I looked at H of 87 mod 7. It equals 87. Yay. Here's my problem. What about 3? If I just check H of 3 mod 7, does that equal 3? No. If it's not equal, what am I going to have to do? Now I'm going to have to do a linear search, a for loop. That's going to be, well, let's use big O because it depends on if it's full or not. But now all of a sudden I've got an O of n thing going on. So when it's not in 3, I'm going to check 4. It's not there. I'm going to check 5. It's not there. I'm going to check 6. Oh, there's where it's hiding. Because 18 got into 5 first, 3 had to skip over both 4 and 5 to get to 6. And what happens on these linear searches, the data starts to group up, starts to bunch up, because as it hits a collision, it's searching for the next open spot. So 18 was easy. It was just one away from where it belonged. But now, whatever comes in here, other than 1, say, something that maps to 2. If something maps to 2, it's going to have to go through the whole array before it gets to that empty spot at 1. So this thing is starting to run a bad runtime, even though there's still room. And that's where we come up with what we call an open hash. This is the technical name, an open hash with separate chaining. Where instead of making a regular array, I'm going to make an array of lists. Trees, heaps, whatever. Generally, a list is fine. So now, when I go to my, what would be a good color for this? Orange. So let me go back to my numbers. They were what? 87, 32, 79, 70, 18, and 3. Okay, that's probably not exactly the order. Is it exactly the order? Oh, cool. I'm having a more lucid day today. So now, instead of putting it directly into the array, I'm going to put them into a list coming off the array. Okay, so H sub I is a dummy node ahead of the list. And we're going to just run a list off it. So 87 is H of 87 mod 7, which we already said was 3. And 32 is going to go into 4. And 79 goes into 2. And 70 went into 0. And 18, well, 18 goes into 4, so what? So here we go. And 3 goes into 3. And at this point, we can put the nulls in. Okay, now, what's the good part about this? Well, how is this better than the closed hash? Everything is still there. The closed hash, I lost 87 and 32. Now I still have them. In what way is this better than the linear probe? There's no linear search. I know where it is. 18 is somewhere in that H sub 4 linked list. Now, is it possible that everything ends up in box 4? Yes. Is it likely that everything ends up in box 4? No. The probability that everything would end up in box 4 is 1/7 to the 6th power. Pretty small. So, by probability, the number of collisions would be the number of the data over the array size. So the number of collisions I can expect would be, I have 6 data and 7 in the array, so it's less than 1 collision per location. I deliberately picked numbers that had collisions. Now, let's go back to the idea of storing QC students by the last 4 digits of their CUNY ID. Okay. Now, do you have any idea how many students there are at Queens College? It's roughly 25,000. If you count the graduate students and the the students that are student teaching at the schools, the law school students that I know they're off campus, but they're right next to us. They're all part of Queens College. All the graduate departments, the grad students that are technically a grad center, but they're working at a Queens College. So we have roughly 25,000 students. How big would this array be if I'm using 4 digits? Ten to the fourth, which is 10,000. So how many expected students would be in the same hash? The expected collisions. 2.5. That's how many we would expect. Is it possible? All right, now here comes, how many of you, I don't know how much statistics you take. Any of you do the null hypothesis stuff? Do they go into that with the CS people? Hypothesis testing? I'm guessing no. They just do basic probability and statistics and stuff like that with you guys. Have you guys taken the probability and statistics yet? So you never heard of a null hypothesis or hypothesis testing? Okay. All right. Well, the idea of hypothesis testing, I'm not teaching you statistics. We can never be 100% positive about anything in statistics. We can see that there's a relationship between things, but we don't know what the relationship is. We don't know what's the cause and what's the effect. We just see a relationship. We can't definitely, well, in computability, you know some of this from computability. 320, how many of you are taking, I think some of you are taking 320. How many of you are taking, hold on, poll time, are taking or have taken 320, theory of computation, or computability theory, whatever we're calling it now? All right, and we're in the last 2 weeks of the course. So the 5 of you who have, remember I'm running right to your 320 teachers and telling on you. No, I'm not. Can you prove that a language does not accept anything? Is it possible to prove that a language is empty? Is it possible to prove that a language is not empty? Well, the question was if you took or are taking 320. I know some of you are because you had a test with Dr. O'Bernick coming up. So you probably started this part, right? You started Turing machines and... Okay, so can I prove that a language is not empty? Can I prove that there is at least one item in a language? Yes. I just try things till I get one. Can I prove a language is empty? I cannot prove it is empty. I can prove it's not empty by finding something. But maybe I just didn't find it yet. Can I prove that the slot machine in whatever casino in Atlantic City is fixed? No. Just because I didn't win yet doesn't mean it doesn't pay off a winner. It just means I didn't get it yet. Because anything that's being done in some kind of random or infinite testing, and this is where your whole idea of finite and infinite come in, maybe I just didn't get to it yet. I mean, at some point we kind of assume maybe something doesn't work, but unless I do an exhaustive search, and if I have strings that are infinite strings, I can't do an exhaustive search. So is it possible that all 25,000 students have the same last four digits? Is it possible? Yes. Is it likely? No. Is it even likely that I have 100 students with the same last four digits? No. If you assume a relatively normal distribution, I should figure, 0 to 5, maybe 10. If the average is 2.5, the probability that there's 100 people with the same last four digits is pretty small. And if it's happening that I've got that many, then my numbers are being handed out wrong. There's something wrong with the way I'm doing the numbers. So something like this, I have such a small number that setting a linked list would be fine. If I used an array of size 1,000, so just using the last three digits, now I've got the expected collisions of 25. At that point, maybe use a binary search tree. Because even if I have 25 people that I'd have to search through, if I use a binary search tree, that's more like, 5 people. Log of 25 is between 4 and 5. So I can set these chains up so that all the data is stored, nothing is lost. This is what you call in the cache, this idea is the set associative. Oops. Just to tie this idea into 343. And this is the fully associative. In the fully associative mapping, or fully associative cache, or linear probe cache, I can use the entire array before I get a collision. Problem is I can't find the stuff because nothing's really where it belongs. It's kind of like your junk drawer. It's a little bit better than the junk drawer because I have the original hash function putting me someplace. The problem is when I can't fit something where it belongs, then I start shoving it anywhere. So there wasn't room for it where it belonged. Stick it somewhere else. And what happens eventually, you can't find anything. In the direct map, everything has a specific place. And if I need something else to go in that space, I just throw out what was already there. I certainly would not want to do that with my banking program. And actually, the project 1++, project 2 idea, is you're just going to take project 1 and make an array indexed by 4 digits or 3 digits, let's go with 3 digits, of the account number. We're not going to worry about collisions. Just don't give two people the same account number. If you want to, you can add that in, extra credit. I'll put that in. You could certainly make an array list. I mean, not an array list, a array of lists. And then some of you already had done something like that. You had talked about it on the name search. But if I know the account number, I can find the customer in definitely one step. If I'm going by name and their name is Smith or Jones or Johnson, then, or Chen, Islam, I'm going to have a lot of people with those names. And it's going to take me a while to find them by name. But if I know the account number, I have it in one shot. If I know your student ID, I find you in one shot. The problem is I don't know your student ID. I have to look it up. So that's why we build in any database like this, we build in the fast lookup, the one-shot hash table idea lookup, but we still need the backup because if I don't know the account number, I have to be able to find you by name. My name is slower, but if I don't know the account number, I have no choice. Does that make sense? It is literally one of the problems I have, like when I'm trying to do grade changes and things like that, because I have to go into back into Blackboard from whatever to find your ID number, or CUNY First to find your ID number, because those forms are filled out by ID number, not by name. And it's why in banks, they do keep, if you've opened up a bank account, you probably don't do it, it's all done on computer now, but they have duplicates of everything. There's a listing, a book, in case the computers are down, there's a book listing by name and a book listing by account number. The fast one is the account number. But if we don't know your account number, first we have to go look it up in the name list so that we can check the balance on the account number list. So that's the idea of using a hash table to store data. So that is not a comparison type of storage. It's not an alphabetical order type of storage. When you try to look up credit card information, credit card accounts, they usually just ask for two things. They ask for the last four digits of your social security number and your zip code. Because with those two pieces of information, the list of collisions is small enough that they can just then check your name quickly. If they just go by zip code, that's a lost cause. If they just go by four digits, you know, even if you're just looking at New York City, you've got what, 9 million people living in New York City? If you just look at Queens, there's like 2 million people, 2.5 million people live in Queens. A million live in Flushing. Just under a million, I think, live in Flushing still. So at four digits, I'm going to have a lot of collisions. But if we add in the zip code, there's several zip codes in Flushing area, that pulls it way down. That both are the same pulls it way down. And it becomes a manageable search. Right, so that's all of our main storage ideas for data structures. We're not going to actually use the hash map structure the way it's written in Java. We're just going to add in our own array that is storing by a hash function. But that's what a hash table is. That's what it does. The interesting thing with when you use hash maps, particularly in Python, I know some of you play around with Python. When you use a hash map in Python, nobody really knows. Because you can take the same data and run it 3 or 4 times in a row on the same program, and the data is in different places. If you just have it print out the mapping, it's in different places. So it's not a consistent map, but it preserves the goal, which is to have an order 1 average lookup time. 2.5 is still order 1. I mean, if we go to the smaller array I have here, on the expected collisions being 25, I would go with the BST, and then we have a log n lookup time. To guarantee no collisions, completely no collisions, you need to have like your CUNY ID, which is an 8-digit CUNY ID, and an array that's indexed to 10 to the 8th. That's an unreasonable amount of space. So for most hash tables, we have to deal with the possibility of a collision, whatever it is. Even though, as I said to you, if we do the birthday thing, if I set up an array of 365 locations for the birthdays, and I have 40 people, I'm going to have a collision somewhere. It's over 90% sure I'm going to have a collision somewhere. So I have to at least provide for it. Whether I say, you know what, it's so rare, let me just do the linear probe. But I mean, it's so easy to just make an array of lists. You've got you wrote a list class. You wrote a stack class. You wrote a queue class. You could use the queue class. That would be fine. Actually, when the original listing, we don't get it in this form anymore, but the original listing of students for a course, if they printed it out exactly the way it's in registrar, is a queue. You're in the order that you registered. That used to be the original list we got, like the first day of class. It wasn't alphabetized yet because people were still registering. So it was just in queue order. Once they were not registering anymore, it went to alphabetized order, but was most likely a linked list. And then once the drop period ends and you're stuck with a grade one way or the other, then it would switch to an array implementation as the fastest way to search for you. So all of these ideas come together. We need to use more than one thing. So this could be, the hash table could be an array of queues, linked queues. We don't know how many are going to be in any one block. We know the average number. You know, our average number on this one was, 1. But we did find we had 2 collisions on 3 and 2 on 4. 2 that mapped to the same location. And not a big deal. It's still constant time. It's 2. Questions on that? I mean, does the hash table seem like actually a pretty good way to handle data? Yeah, I mean, the definite downside is that you have to watch out for the collisions. And of course, um, you need to come up with a function. I don't know if any of you still get like magazines, paper magazines, not, an online thing. Anyone still get magazines delivered to their house? Because magazines had a printed label on them. Well, I still get my New Yorker in paper. I have it online too, but it's not the same as reading it in paper. But that's because I'm old. I'm sorry. But magazine covers, or even, like Union newspapers and that, they have a label on them, and it's your regular printed address and your name and everything. But in the corner, there's a code, and it's usually like one or two letters from your last name, and then it's got your zip code in it, and then there's a couple of other digits. And it's what they use to look up your information quickly. Because, a nationwide magazine like Time or Newsweek, they have, millions of subscribers. So they need a quick lookup system. And that's what they did. They built something that can easily be converted to a bit format and be hashed easily. And again, when we're talking about like radix sort, um, it's basically hashing by bits. It groups the bits, and that's how it hashes. And again, those of you who already took 340, that's how the cache allocation works, right? You use block numbers and tag numbers. You use a specific block in the main memory to get a tag number. You find a location, the cache block that it's going to map into, and you identify it by the tag number, so that you have an easy, you don't, your whole address is never used. Parts of the address are used, and only the MIPS step would actually look at the um, location within the cache block. One of the things I like about this time of year is you find all of the courses meeting. 313 and 343 come crashing into each other at the end of the course when you're doing cache and you're doing hash tables. All right, the next three classes are going to be basically graph stuff. Implementing the graph and writing code for the graph. I know you did a lot of graphs in 220. I'm not going to be talking about, or maybe just a little bit, talking about actually implementing Dijkstra or Prim or Kruskal, but we will talk about finding the minimum edge or finding a distance to a vertex, um, depending on how we represent the graph. So we'll look at how graphs are represented on a coding level. Believe it or not, it's either an array or a linked list or a hash table. There you go. I just summed up the next three classes easily. I'm thinking of next, not this week, next Friday, scheduling a review session in the morning for 313. And, if you can't come, I'll record it. But since people feel, I don't really know why you need a review session since every recording is up online. But I guess we're desperate times, desperate measures. Okay. Please, again, if you see your friends, please impress upon them that it's important to be a class. Because, there's 14 here today, and that's ridiculous. There's 32 people registered, and only 14 came to class. So, okay, and I know there's a couple of you that weren't able to make office hours, and I'm trying. It's just I've had a lot of meetings the last week or so about it's curriculum related stuff, so it's not planning a party. They're important meetings, and that's why I've been a little hard to. I'll put up a list for this week, but if Fridays are not good for you, you have to let me know. I'll try. But, again, there's a limit to how many hours I can do. I mean, it's just a physical limit. I can't get grading done. I'm behind on grading. We know that. I haven't looked at the project one stuff yet, except things that were questions, because I'm still putting up the breakout group stuff and enabling the part C of your warm up. So, when I'm spending 15, 14, 15 hours a week doing office hour type stuff, it doesn't leave me a lot of extra time. Office hours are supposed to be an hour or two a week, and I give you guys all day Friday. I'm giving up the break between classes on free hour. Last night I was working on office hours between 6 and 8 o'clock, so, Saturday mornings, it's a little daunting. Okay, so anyway, I will see you maybe on Friday, office hours. I'm going to put up, the form will be up like it's been. Tomorrow it'll go up, it'll be in content, same way. 2 minutes is about what I've got, yeah, because I have another class. And I think just from the feeling of my throat, which is like I swallowed broken glass, they may be seeing this, but all right. So anyway, the form will be up tomorrow for office hours, and I will put up like a calendar of the next couple of classes. Okay. All right, guys. Remember, if you didn't check, oh, that's right. You guys, you were the only class I got the data right after your class. The final is in Remsen Hall, 100. The Remsen is right next to the science building, the other side of the gate. On December 14th, 11 to 1. Okay, it's a big, big room, so, it's a good sized task table for everybody. Okay, so we have Remsen 100 on December 14th from 11 to 1, and then it's over with. Your projects will be due like that Friday, the 17th. So you'll have a couple of extra days to get the project. Yeah, it's the 14th, because I put all of you together. The 14th is reading day. There are no classes on the 14th. Yeah, Remsen 100. 11 to 1. Yep. All right, guys. Take care.
Hey, Professor. I just wanted to, since we were talking about like hash tables and stuff, I wanted to share. I remember I told you